In this video, we'll talk about multiple comparison concepts. So, we'll start with example of one single experiment. So let's say we are doing a single experiment in we are comparing a drug with a placebo, and we already know that the null hypothesis is true in this case, which means that we already know that the effect of the drug is no different from the effect of placebo. So the null hypothesis is already true in this case. Now if we take an alpha level or significance level of 0.05, what does it mean? It means that assuming that the null hypothesis is true, there is a 5% chance that we will still conclude that we will still get a significant p-value. So that is the meaning of taking an alpha level of 0.05 or a significance threshold of 0.05 in this single experiment, is that when we already know that the null hypothesis is true, there is a 5% chance. 0.05 means 5%. So there is a 5% chance that we will still get a significant p-value, means we will get a false positive result. So there is a 5% chance of getting a false positive result, which is what you also called type 1 error. And there is 95% chance that the p-value will not be significant, what it should be, right? Because we know that null hypothesis is true in reality. So there is a 95% chance that the p-value will not be significant, or it will be more than 0.05. So this is what you call true negative. Means why true negative? Because we know that null hypothesis is true in reality and the p-value is also not significant, so it is true negative. So basically when I take an alpha level of 0.05 for 5% in any experiment, it basically means that there is 5% chance of false positive, means type 1 error, and 95% chance of true negative. Okay, so I have written this here. There is a 5% probability that the p-value will be significant if null hypothesis is true. This is the meaning of the alpha level. And what is 95%? 95% is the probability that if the null hypothesis is true, and p-value will also be non-significant. So that is your true negative rate. Okay, now we have to talk about multiple comparisons. So what happens if instead of doing a single experiment like this, in this case we are talking about a single comparison or single experiment, what happens if I start to do multiple comparisons? So if I for example, let's assume I'm making 3 independent comparisons like this. Okay, so I have 3 experiments. In all 3 experiments, again same, null hypothesis is that the drug is same as placebo, but instead of 1, now I'm making 3 comparisons. So when I make 3 comparisons, you can understand that provided that I take the alpha level of 0.05 in each of these comparisons, the true negative rate will be 95% for each of these experiments, right? For these 3 experiments, true negative rate will be 95%, 95%, 95%. So the cumulative true negative rate will be 95% to the power 3. Or you can also write this in the form of fraction, 0.95 raised to the power 3. So it will be basically 90%, right? So that is the true negative rate for 3 independent comparisons. So what does it mean? It means that there is 90% probability that all the 3 comparisons will have non-significant value when null hypothesis is true in reality, right? So this is the true negative rate for all 3 comparisons combined. It is the probability that when in all 3 experiments, the null hypothesis is true in reality, p-value will also be non-significant in all 3 experiments. So if I subtract this true negative rate from 100%, I will get the false positive rate for these 3 experiments. So that will be 100 minus 90, or 10%. So this 10% is the cumulative false positive rate for making 3 independent comparisons. So 10% probability that at least one that out of these 3 comparisons, at least one comparison will give a significant p-value if null hypothesis is true for all the 3 comparisons. So this kind of false positive rate, which is given for multiple comparisons or 3 comparisons in this case, this is called as a family wise error rate. Okay, if you have not understood, I will give you one more example. Let's say we are doing number of comparisons. So instead of 3 you can assume 4, 5, whatever you want to. Then the true for each of these comparisons we are taking a significance level of 0.05 or 5%. Then combined true negative rate will be, you can understand, it will be 0.95 to the power k, and combined false positive rate will be 1 minus 0.95 to the power k. So this is basically the combined false positive rate for these multiple comparisons, and it is called family wise error rate. And how to interpret this family wise error rate? As I have told you, in previous example it was 10%. So it means that there is a 10% probability that at least one out of these three comparisons, minimum at least one out of these three comparisons, would give a significant p-value, given that null hypothesis is true for all the three experiments. Okay, so in this what is family wise error rate? It is the probability that at least one comparison out of the multiple comparisons that you are doing will give you a significant result if null hypothesis is true in reality for all the comparisons. So this is a graph you can see, which we have on x-axis we have number of comparisons, and on y-axis we have the probability of getting a significant p-value. So you can understand, as the number of comparisons increases, probability of getting at least one significant p-value just by random chance increases. And you can note that for example, we took an example of three independent comparisons, and you can see when we are doing 5 independent comparisons, the family wise error rate is near about I would say 20% or something, right? And when it is 13, number of comparisons is 13, the family wise error rate is approximately 50. So when you're making 13 independent comparisons, there is at least a 50% chance, there is 50% chance that at least one comparison out of those 13 comparisons could have a significant p-value, even if the null hypothesis is true in all the 13 experiments. Similarly, you can see this number 45. So when you are doing 45 comparisons, the family wise error rate is near about 90%. So this is an interesting graph. You can note, as the number of comparisons increases, the FWER increases, right? So this is another table showing you same thing. As the number of comparisons is increasing, FWER keeps on increasing. At about 13 comparisons, the FWER is about 50%, and at 45 comparisons or so, it is about 90%. Okay. So I'll give you one interesting example of this multiple comparisons in real life. So Bennett and colleagues, they dramatically demonstrated the problem of multiple comparisons. They used fMRI to map blood flow in thousands of areas of brain. Their experiment subject was shown a photograph of a person and asked to silently identify which emotion the person in the photograph was experiencing. The investigators measured blood flow to thousands of areas of brain before and after presenting photograph to the experimental subject. In two particular areas of brain, blood flow increased, and those p-values were highly statistically significant. So this sounds compelling, right? The investigators have identified regions of the brain involved with recognizing emotions, right? Nope. Why? Because the investigators could prove beyond doubt that the findings were actually false positive from noise in the instrument and were not caused by changes in blood flow. How could they be so sure? Because their experiments were actually dead. They were dead salmon. So this is the problem of multiple comparisons. When you are making so many comparisons, there is very good probability that you can get at least one comparison to be statistically significant just by random error or random chance. Okay, so when they so you need to do correction for these multiple comparisons in your manuscript. That's the main issue. So when these experimenters, they corrected for these multiple comparisons to account for thousands of brain regions which they looked for, neither finding was statistically significant. So this p-value you see, which was significant, less than 0.001, it is actually before correction. Okay, and because these experimenters, they did so many multiple comparisons and they did not correct for the p-value, that is why this p-value is significant. When we will correct for this so many multiple comparisons that were done, they did more than 1,000 comparisons actually. So in that case, FWER would be near about 99% or something. So it's highly likely that at least a few of the comparisons would be statistically significant just by random chance. So you have to correct for these multiple comparisons. Now here is another question: when is it okay to do multiple comparisons in your manuscript? So there are some instances when it might be okay to do these multiple comparisons. First is corrections for multiple comparisons not needed if people reading the data take into account the number of comparisons. So some statisticians, they recommend that investigators never correct for multiple comparisons, but instead they report uncorrected p-values and confidence intervals with clear explanation that no mathematical correction was made for multiple comparison. The people reading the results must then informally account for multiple comparisons. So one idea is that you don't have to do correction for multiple comparisons. You can just tell in your manuscript how many comparisons you actually did and how many of them came out to be significant. So that is one informal way of accounting for multiple comparisons. So let's say you are doing maybe 100 comparisons in your manuscript, and then the readers of the manuscript can informally account for multiple comparisons, because we know that the significance threshold is 5% in each of these 100 comparisons. So there is a 5% chance, there it means, how to interpret this 5% is basically, out of these 100 experiments, 5% experiments can be statistically significant just by chance, even if null hypothesis is true for all the experiments. So what is 5% of 100? It is 5, right? So it means if I do 100 comparisons, I can expect at least 5 experiments to have a significant p-value just by chance. Without just by chance means just by sampling error. Okay, so this is an informal way to account for multiple comparisons. So I will read it. If all the null hypotheses are true, means out of all of these 100 experiments, let's assume all the 100 null hypotheses are true, then we will still expect 5% of comparisons to have a uncorrected p-value of less than 0.05. Means out of these 100, at least 5 experiments can have a significant p-value even if null hypothesis is true for all the 100 experiments. Now you can compare this number with the actual number of small p-values. So let's say we did 100 comparisons and we got maybe 4 p-values were significant out of 100 comparisons which were made. Now this definitely doesn't mean much, because we know that at 5 comparisons can be significant just by chance. So this 4 doesn't mean much. Okay, so that's an informal way to account for multiple comparisons. But this approach requires that all the comparisons, or at least the number of comparisons, have to be reported. So this requires that in the manuscript you report how many comparisons you made or the investigators made. So they cannot report just the four, let's say they got 4 comparisons as significant. It would be unethical to report just only those 4 comparisons. They will have to report that they did actually 100 comparisons, and out of those 100 comparisons, 4 comparisons came out to be significant. So it requires that the authors of the manuscript, they report how many comparisons, total number of comparisons they performed, not just how many comparisons they got as significant. Okay. Then second way when corrections may not be needed for multiple comparison is when you have clearly defined one outcome as primary and some other outcomes as secondary. So many clinical trials, they actually define as part of study protocol that one outcome is primary and there are some secondary outcomes, right? So it may be okay when you have single primary outcome and multiple secondary outcomes. It may be fine to not correct for these multiple comparisons. Okay. Third is correction for multiple comparison may not be needed if you make only a few planned comparisons. So the key word here is planned. They should be pre-planned. Whatever comparisons you are doing, they should be pre-specified in the protocol of the study. So let's say you collect a lot of data and you may want to focus on only a few scientifically sensible comparisons rather than every possible comparison. So that is that is what is meant by planned comparison. So these comparisons, they must be planned as a part of experimental design. It is cheating to look at the data and then decide which comparisons you wish to make. When you make only a few pre-planned comparisons, many statisticians think it is okay not to correct for multiple comparisons. So basically, let's say you have planned 7 comparisons or 8 comparisons or whatever, 9 comparisons in your study, and it has been pre-specified in your protocol, then it may be okay to not correct for those p-values. But the key word here is they should be pre-planned and pre-specified in your protocol, right? You cannot start hypothesizing for new endpoints or new comparisons after looking at the data. That is important. Okay. Then fourth condition is correction for multiple comparison not essential when results are complementary. So what is meant by complementary or consistency of results? We will take an example. See, Riddler and colleagues asked whether lowering LDL cholesterol would prevent heart disease in patients who did not have high LDL cholesterol, did not have previous history of heart disease, but did have some abnormal blood tests suggesting the presence of some inflammatory disease. So this is the study question they are asking. The study included almost 18,000 people. Half received a statin to lower LDL cholesterol and half received a placebo. So the investigators' primary goal, which was planned as a part of protocol, was to compare the number of endpoints which occurred in the two groups, including deaths from heart attack, stroke, non-fatal heart attacks and strokes, and hospitalization for chest pain. So you can see they have planned quite a number of primary endpoints, right? So these events happened about half as often in people who were treated with the drug compared to people who were taking the placebo. So according, as far as the primary endpoint is concerned, it looks like the drug is working. Even though there were multiple primary endpoints, the drug is showing some consistent result for across all these endpoints, right? The investigators also analyzed each of the endpoints separately. So those people taking the drug comparing with those taking the placebo had fewer deaths, fewer heart attacks, fewer strokes and fewer hospitalizations for chest pain. The data from various demographic groups were also analyzed separately. Separate analysis was done for men, women, old, young, smoker, non-smoker, people with hypertension, those without hypertension, people with family history of heart disease and those without family history of heart disease, and so on. So they have also done so many subgroup analysis also. About 25 subgroup analysis was planned in total, right? But the key point here is and also the investigators, they made no correction for these multiple comparisons. So they have done subgroup analysis also. They have done at least 25 subgroup analysis, and the number of endpoints they took were also quite many, like deaths, heart attack, stroke, hospitalization, right? So this is a classic example of multiple comparison. But despite that, the investigators have not corrected for these multiple comparisons. The reason is the reader does not need to try to informally correct for multiple comparison, because the main reason is that the results were very consistent. Means that the drug showed superior benefit over placebo in almost all the analysis. So multiple comparisons each ask the same basic question, and all the comparisons, they actually lead to the same conclusion, that people taking the drug had fewer cardiovascular events than people taking the placebo. So in contrast, correction for multiple comparison would be essential if the results showed that the drug worked in few subsets of patients but not in other subsets. So the point which I wanted to put across is the results should be consistent across all the comparisons. If the results are consistent across all the comparisons that you have made, then it may be okay to not correct for those multiple comparisons. So what are the 4 conditions in which it may be okay not to correct for multiple comparison? First is, one is obviously to never correct for multiple comparisons. Just tell in your manuscript how many comparisons you have done and how many of them were significant, and the readers of the manuscript can informally account for those multiple comparison. Second is, when you have only one primary outcome and multiple secondary outcomes, it may be okay because the primary outcome is still one. So it may be okay to have multiple secondary endpoints and do multiple comparisons. Third point should be, all the comparisons that you are making, even if you are making multiple comparisons, they should be pre-planned and pre-specified in your protocol. Then it may be okay to do multiple comparisons and not correct for multiple comparisons necessarily. And fourth condition situation is when the results are very consistent across all the comparisons, then it may be okay to not correct for those multiple comparisons. Okay. So now again we will come back to our FWER, false family wise error rate, and we'll understand the interpretation. So let's assume we are doing 1 2 3 4 5 multiple comparisons, and significance level is 5% in each of these multiple comparisons. I have not corrected for these multiple comparisons. So what does this 5% mean? It means that out of these 5 comparisons, 5% out of these X number of comparisons that I have done, 5% comparisons can be statistically significant just by chance. So I gave you example of 100 comparisons. If in 100 comparisons, for 100 comparisons, the alpha level is 5% in each of these comparisons, it means that 5 comparisons could be statistically significant just by chance, even if null hypothesis is true for all these experiments, right? So 5% experiments can be statistically significant just by chance, even if NH is true for all of them. Another term you need to know is FWER. So how to calculate FWER for 5 comparisons? You know that the true negative rate will be 0.95 to the power 5. So 77% chance that no comparison will be significant if all NH are true, right? And FP or FWER will be 1 minus this 1 minus 0.95 to the power 5, so it will be 23%. So this is the FWER for 5 comparisons. So how to interpret FWER? It means that there is a 23% chance that at least one of these comparisons could be statistically significant just by chance, even if NH is true for all the 5 experiments. Okay, so again, same thing, another example. Let's say we are doing a single comparison, just one comparison, not multiple comparison, and alpha level is 5%. So this alpha level or 5%, this is called as the per comparison error rate, because for one comparison the false positive error rate is 5%. So per comparison error rate is 5%. So how to interpret this? It means that there is a 5% probability that p value will be significant even if NH is true in reality just by chance or random error. So there is a 5% probability of getting a false positive, means significant p value, even if null hypothesis is true for this single comparison, right? And when I am doing multiple comparisons, the interpretation of this alpha level changes. Okay, so the interpretation of alpha level is pretty straightforward when I'm doing a single comparison. When I'm doing multiple comparison, the interpretation of alpha level in each of these comparisons is 5%. It means that there is a 5% of these experiments could be statistically significant. Okay, so that is the interpretation of 5%. Okay, and of course when I combine this and calculate a FWER, false family wise error rate, then what is the interpretation of that family wise error rate? It is that, let's say the family wise error rate comes out to be 5%, just assume, then it means 5% probability that at least one of these comparisons will be statistically significant just by chance, even if all the null hypotheses are true. Okay, so again we'll take a few more examples. So one more thing, what is family of comparisons? Because we're talking about family wise error rate, so we need to talk about what is a family. So usually a family consists of all the comparisons in one experiment, or all the comparisons in one major part of the experiment. So this is a little bit ambiguous thing to decide what is a family of comparisons. Usually all the comparisons that you're doing in your single experiment, those together, they will be called a family of comparison. So when reading for the results, let's assume you're reading a manuscript and the results have been corrected for multiple comparisons, then you need to go back and look for how many comparisons it has been corrected. Has it really been corrected for all the comparisons that were made in the manuscript, or only a part of the comparison that were made in the manuscript? So how are the authors of the study defining the family of comparisons? That is important. Usually all the comparisons made in a single experiment, they count as the family of comparisons. So you need to ask about how the investigators, they have defined the family of comparison. Imagine you have made 20 comparisons. This is a exercise for you. Try to pause the video and try to see how will you interpret this this case. Okay, let's say you have 20 comparisons, and let's assume all the 20 null hypotheses are true, and for all these 20 comparisons the significance level is 5%. Then how to interpret this 5%? The interpretation of 5% is that 5% of these 20 comparisons can be statistically significant just by chance, even if null hypothesis is true. Then pause the video and calculate the FWER for 20 comparisons. You know how to calculate FWER for 20 comparisons. It will be 1 minus 0.95 raised to the power 20. So that will come out to be 65%. So it means that there is 65% probability that at least one of these, one or more than one, at least one of these comparisons out of 20 comparisons can be statistically significant just by chance, even if null hypothesis is true for all the 20 comparisons. Okay, so I hope by now the interpretation of 5% and the interpretation of family wise error rate is clear. Okay, so now we will come to corrections. So I will only discuss two types of corrections. First type of correction is the Bonferroni correction. You may have heard of it. It's the classic example, it's the most common type of correction that is done for multiple comparisons. And the second type of correction I'll talk about is the correction with respect to the false discovery rate. So if for Bonferroni correction, it's very easy. What you have to do is, in the idea of Bonferroni correction is that the family wise error rate should be controlled at 5%. Okay, so we want to keep the family wise error rate. What is the family wise error rate? It is that if family wise error rate is X%, it means that there is X% chance that at least one or more than one of these comparisons could be statistically significant just by chance, even if NH is true for all the comparisons that we have done. So we want to control family wise error rate at usually 5% or whatever is your desired level. That is the purpose of Bonferroni correction. So we'll take an example of 20 comparisons. Let's assume we are doing 20 comparisons, and let's assume we want to maintain the FWER at 5%. 5% means 0.05. So we want to maintain the FWER at 0.05. Then how do you do Bonferroni correction? You will just divide this desirable family wise error rate, which is 0.05, by the number of multiple comparisons. So it will come out to be 0.0025. So this is now your new significance threshold for each of the comparisons. It means that when you do 20 comparisons, only when p-value is less than 0.0025 for each of these comparisons, then that comparison will be considered a statistically significant comparison. Okay, so a particular comparison will be considered statistically significant only if p-value is less than this. Okay, less than 0.0025, or you can also call it alpha by k. Okay, so I'll show you how this, by doing this kind of correction, we are able to maintain the FWER at 5% or whatever your designated level is. So let's assume we are taking an example of 20 comparisons. Let's assume we have done the correction, right? We have done the correction means now the new significance threshold is 0.0025. Now I want you to pause the video once, and by taking a significance level of 0.0025, calculate the FWER. Okay, previously without correction, what was the alpha level? It was 0.05. Calculate FWER whilst having a alpha level of 0.05, and also calculate FWER whilst having a alpha level of 0.0025. Okay, so in this case, in case of let's first calculate without correction. So without correction, true negative value will be 0.95 raised to the power 20. So that will be 36%, and family wise error rate will be 1 minus 36%, 100 minus 36%, that is 64%. So 64% is the family wise error rate when we have not done any Bonferroni correction. Now once you have done the Bonferroni correction, you can see the true negative rate will be 1 minus 0.0025. Am I right? That will be the true negative rate for one comparison. So that will be 0.9975. For 20 comparisons, it will be 0.9975 raised to the power 20, or near about 95%. And false positive rate or family wise error rate, that will be 100 minus 95, near about 5%. Okay, so you can see how by doing Bonferroni correction we have maintained the FWER at 5%, right? You can just pause the video and try it yourself. So this is the same thing which is written here in this table. You can see that the true negative rate has actually changed to 95%, and family wise error rate has changed to 5% after doing the Bonferroni correction. You can similarly do one more exercise. You can see, let's say we are doing Bonferroni correction for 3 comparisons, and then you can compare before and after correction what is the FWER. So before correction, you know that alpha level will be 0.05, right? And after correction, what will be the new significance threshold per comparison error rate? This is something we call per comparison error rate. So the per comparison error rate after Bonferroni correction will be 0.05 divided by 3, right? So that will be 0.06. This is the per comparison error rate after correction, and before correction it was 0.05. So now you can calculate FWER for each of these cases and you can compare. First we will calculate for the uncorrected case. In uncorrected case, true negative will be 0.95 to the power 3, which will be 85%, and FWER will be 15%, right? After correction, you can see true negative rate will be 1 minus 0.016 to the power 3, right? So that will be the true negative rate, which will come out to be about 95%, and FWER will come out to be 5%. So you can do these exercise to see that after doing Bonferroni correction, the family wise error rate is actually maintained at about 5%, right? So remember, when you doing Bonferroni correction, the new threshold that you will get, for example, in this case it will be 0.05 divided by 3, that is 0.06. This is called as the per comparison error rate, but the entire family wise error rate, the FWER, is still 5%, right? So in Bonferroni correction, the alpha level or the significance level or FWER is still 5%, but what we have changed is the per comparison error rate. The per comparison error rate is nothing but the threshold for each individual comparison that has been changed to alpha by k, or alpha means 0.05 by number of comparisons. Okay, then I'll give you one example of one case, one common type of experiment where we doing this kind of correction, Bonferroni correction. So that is genome-wide association studies. So in genome-wide association studies, basically we have a disease group and a control group, and we are often comparing the prevalence of a particular single nucleotide polymorphism between the disease and the control group. And we are doing multiple comparisons in this way because there are so many SNPs, and the prevalence of, for example, 10,000 or 20,000 or 1 lakh of SNPs you will be comparing between two groups. So this is a classic example of multiple comparisons, right? So you have a disease group, you have a control group, and you are comparing the prevalence of disease and control group, the prevalence of SNPs between the two groups, right? So I will just read it for you. Genome-wide association studies, they use the Bonferroni correction to cope with huge number of comparisons. These studies, they look for association between the disease or the traits and genetic variants, usually single nucleotide polymorphisms. So they compare the prevalence of up to 1 million of SNPs between cases and controls. So there are so many comparisons, millions of comparisons that you are doing in a genome-wide association study. So how to correct? It's very easy. You will just divide 0.05 by the number of comparisons that you are making. So let's assume you are making ones, tens, 100,000, 10,000, lakh, 1 lakh. So let's assume you are making 1 lakh comparisons. Then your new per comparison error rate, it will be 0.05 divided by this much, right? So this, for example, will be your new threshold level for single comparison. So a tiny p-value, a p-value less than this, will be is evident that the prevalence of a particular genetic variation differs in the true group that you are studying. So this will be the new threshold for deciding whether a p-value is significant or not. So this is one classic example of Bonferroni correction. Okay, so now we'll talk about one more type of correction, which is the correction with respect to false discovery rate. So remember, what we were doing in Bonferroni correction is we were controlling the FWER, and you know what was FWER. FWER, for example, if FWER is X%, it means that there is X% probability that at least one of these comparisons will be significant just by chance if all the comparisons, they have a their null hypothesis is true in reality. So that the purpose of Bonferroni correction was to control the FWER. But then there is another kind of correction, which is the correction for false discovery rate. In this case, rather than controlling the FWER, we are actually controlling the false discovery rate. So what is false discovery rate? Let's assume we are doing an experiment, and okay, I'll explain with this term only, false discovery rate. It's very evident. False discovery rate means, let's say you have done a discovery. What is the discovery? Discovery means you have a significant p-value. So let's say you have a discovery, means you have a significant p-value. What is the probability that it is false? What is the probability that null hypothesis is true? See, this is not the same as alpha level. Let's assume we have, let's assume here I am putting significant p-values, and here I am putting non-significant p-values. Here the null hypothesis is true in reality, here the null hypothesis is false in reality. Let's say you have null hypothesis true in reality, and you are getting a significant p-value, that is type 1 error. Let's say you have null hypothesis false in reality, right? So your p-value must be significant, but you're still getting non-significant p-value. That is also an error, that is called type 2 error, right? And these two are not errors. Now what is the difference between alpha level and false discovery rate? They look very similar, but they are very different from each other. So what is alpha level? Alpha level means, let's assume the null hypothesis is true in reality. So look at this part. Let's assume the null hypothesis is true in reality. What is the probability that your p-value is still significant? Means that you have committed an error, and despite the fact that null hypothesis is true in reality, you are getting a significant p-value, right? So this is your alpha level. So in this case, alpha level will be, let's say this is A and B, alpha level will be A by A plus B, right? A by A plus B, that is your alpha level, or 0.05 classically, right? So that is your significance threshold or alpha level. But false discovery rate is a little bit different. False discovery rate is, you have to ask the question, let's say I have made a discovery. Let's say out of all the experiments in which I am getting a significant p-value, let's say there are 100 experiments, total 100 experiments in which I am getting a significant p-value. What is the probability that I am wrong? Means null hypothesis is actually true in reality, right? So in this case, false discovery rate, let's assume this is C, false discovery rate will be A by A plus C. Okay, so I hope you are able to understand the difference between alpha level and false discovery rate. They look similar, but they are very different. The question alpha level asks is, if the null hypothesis is true in reality, if the null hypothesis is true in reality, what is the probability? If the null hypothesis is true in reality, what is the probability that I have committed an error? Means my p-value is significant despite the fact that null hypothesis is true in reality. So that is the alpha level. But what is false discovery rate? False discovery rate asks, if I have received a significant p-value, if my p-value is significant, what is the probability that I have committed a mistake? Means that in reality the null hypothesis is true. Okay, so I will tell you once more. Alpha level is the probability of committing an error when null hypothesis is true, but false discovery rate is the probability of committing an error when the p-value is significant. Okay, or you can say alpha level means probability of getting a significant p-value when null hypothesis is true, but false discovery rate is probability of null hypothesis being true when p-value is significant. So they are little bit different concepts. Okay, so again, what is false discovery rate? It is when I made a discovery, means my p-value is significant. What is the probability that it should not have been significant? In reality, null hypothesis is true. So by doing this kind of comparison, I can actually control the false discovery rate. Okay, so discovery means significant p-value, false discovery means when the null hypothesis is true in reality. So again, the same thing. What is positive FDR definition? Positive false discovery rate definition: if the comparison is classified as a discovery, means if the comparison is having a significant p-value, what is the chance that null hypothesis is true in reality? Or you can ask, of all the discoveries that have been made, means of all the comparisons in which p-value is significant, what proportion of them is expected to be false? So let's say I want to control in, I will tell you how to do correction. It's very straightforward, but let's assume I am denoting the FDR here by Q. So let's say Q is 10%. What does it mean? It means that let's say there are 100 experiments in which p-value is significant, and if there are 100 comparisons in which p-value is significant, then in 10 comparisons that will be false. In 10 comparisons the null hypothesis will be true. Okay, so if Q is 10, it means that of all the discoveries you have made, discoveries means of all the comparisons in which you have received a significant p-value, maximum 10% can be false. Maximum 10% null hypothesis will be true in reality, whereas in the rest 90% of the experiments the null hypothesis will actually be false in reality. Okay, I hope this is clear. I will tell you once again. So when Q is 10% means the F false discovery rate is set at 10%. In this correction, it means that I'm controlling the FDR at 10%, means of all the 100 experiments in which p-value is significant, in maximum 10 experiments it will be a false significant, means the null hypothesis will actually be true in reality, and in the rest 90 experiments the null hypothesis will be false in reality only. So it will be a true positive in a way, right? Means p-value is also significant and null hypothesis is also false in 90% experiments, but in 10% experiments it will be a false positive, because it will be significant, the p-value will look significant, but null hypothesis will actually be true in reality. Okay, so that is the meaning of controlling FDR. So now let's talk about the idea of doing the multiple comparison whilst controlling the false discovery rate. Okay, so we have already understood the concept of false discovery rate. While analyzing a set of p-values, you can set the false discovery rate to a desired value, and that is abbreviated as Q. So let's say you set Q at 10%. What does it mean? It means that your goal is that for out of 100 discoveries, at least 90% discoveries will be true and no more than 10% discoveries will be false discoveries. Means maximum 10% discoveries will be false. If you are getting significant p-value, that is the definition of your discovery, maximum 10% comparisons will be false discoveries. It means in maximum 10% comparisons the null hypothesis can be true in reality, and in the rest 90% of the discoveries they will be true discoveries, means the null hypothesis will be false in reality for those 90% of discoveries, rest 90% of discoveries. So obviously you will never know which is which, but that is the idea of controlling the false discovery rate. So this was I'm going to tell you is a method developed by Benjamini and Hochberg. They set the threshold values for deciding when a p-value is low enough to be deemed a discovery. So how to decide the threshold values with respect to this method? In this method, you will have a different threshold value for each comparison. So unlike in Bonferroni correction, there was a single threshold for each of the comparison. If you remember, in Bonferroni correction, we will just divide the alpha level, whatever family-wise error rate we want. Let's say we want a family-wise error rate of 0.05, then that will be divided by the number of comparisons, and this will be the same threshold for all the comparisons. But in the case of FDR, in case of false discovery rate, the threshold is actually different for different comparison. Okay, and how do we decide that? Basically, we will arrange all the comparisons in terms of p-values. So I'll give you an example. Let's say we have done 100 experiments, 100 comparisons, and in 100 comparisons we are getting 100 p-values obviously, and then you will arrange these p-values in increasing order. So p1 will be the smallest p-value and p100 will be the largest p-value. Then the threshold for determining which p-values are significant will actually be different for each p-value. So the threshold will be lowest for the smallest p-value, but the threshold will be highest for the largest p-value. So what I want to tell you is that in this method, in this FDR method, the threshold itself varies from one comparison to other comparison. The threshold is small for those p-values which are small. The threshold is large for the larger p-values. Okay. So to make a sense of this comparison, why we are doing like this, let me tell you what we do first, and then I will tell you how does it make sense. So let's take the example of 100 comparisons. You have arranged the p-values in increasing order. So P1 will be the smallest p-value that you are getting, and P100 will be the largest p-value that you are getting in the 100 comparisons that you have done. How will you decide the threshold? First you have to decide how much FDR you want. Let's say in this example I want FDR of 10%. You can also set it up at 5% or whatever you want. So what it means, as I've explained, it means that out of all the discoveries made, maximum 10% discoveries can be false discoveries. Means in maximum 10% discoveries, null hypothesis can be true in reality. So I have set the FDR at 10%. Now I will decide the threshold for each of these comparisons. It's very easy. First comparison is, so for first threshold will be 1 out of 100. Why 100? Because there are total 100 comparisons multiplied by FDR. For second p-value, it will be 2 by 100 into FDR. For third largest p-value, for like this is the smallest and this is bigger, this is much bigger, and p100th will be the largest p-value. Okay, so for p3 it will be 3 by 100 into FDR. For largest p-value it will be 100 by 100 into FDR. So it will be same as FDR. So these are your thresholds. These are your thresholds. So let's assume FDR is 10%. So the threshold for first will be 10% means 10% will be 0.1. So 0.1 into 0.01, right? It will be 0.1 into 0.01 because 1 by 100 is 0.01. So that will be 0.001. So this will be the threshold for first. Like that you will calculate threshold for each of these comparisons. Okay, one more example we can take. Let's say we are doing 50 comparisons and I want to set FDR at maybe 5% this time. So how I can calculate? First I will arrange the p-values from smallest to largest. So this will be my smallest p-value and this will be the largest p-value. First I will calculate the p-values and I will arrange them from smallest to largest. Then I will calculate the threshold for each of these p-values. For the smallest p-value, threshold will be, because there are 50 comparisons, so it will be 1 by 50 into 5% because FDR is set at 5% in this case. Then for second it will be 2 by 50 into 5%. For last it will be 50 by 50 into 5%. So that is how you decide the threshold. Now why we are doing like this? Maybe it will start to make sense after reading this. So the reason we are doing this is, let's say you have 100 experiments and for all these 100 experiments you already know that the null hypothesis is true, right? Let's assume for all these 100 experiments you know that the null hypothesis is already true. Then how do you expect these p-values to be? You expect these p-values to be completely randomly scattered between 0 to 1, and the median p-value you expect to be 0.5. Okay, so I'll just read it out, hopefully it will make sense. See, the threshold is actually tiny for the comparison with the smallest p-value and it is much larger for the comparison with the largest p-value. This much you have understood. To understand why this makes sense, imagine that you computed 100 p-values and all the null hypotheses were true in reality. Then you would expect these p-values to be randomly distributed between 0 and 1. It would not be at all surprising for the smallest p-value will be 0.01. Smallest p-value you would expect to be 1 by 100. So smallest p-value will be 0.01. You would expect the smallest p-value to be 0.01 and you would expect the median p-value to be about 0.5. So basically when you already know that the null hypothesis is true in reality for all the 100 comparisons, you would expect the p-values to be distributed between randomly distributed between 0 and 1, and the smallest p-value will be 1 by 100 and the largest p-value will be 100 by 100, right? And the median p-value will be exactly in between 0.5. Okay, so it makes sense to first of all rank these p-values from low to high and then use these ranking to decide the threshold. So here is a brief explanation of how thresholds are determined. If all the null hypotheses are true, you would expect p-values to be randomly scattered between 0 and 1. Half will be less than 0.5 and half will be more than 0.5. 10% will be less than 0.10 and so on. Now let's imagine that you are making 100 comparisons and you have set the desired FDR to be 5%. If the null hypothesis were true in reality, you would expect the smallest p-value to be 1 by 100 because you are making 100 comparisons. So you will expect the smallest p-value to be 1 by 100. Now you will multiply this 1 by 100 by q, that is your 5%. So the new threshold will come out to be 0.0005. Similarly, you would expect the second smallest p-value to be 2 by 100, right? Because we are expecting the p-values to be randomly scattered between 0 to 1. So the second smallest p-value, you expect it to be 2 by 100, and then you will multiply it with the false discovery rate, which is the 5%, to get a new threshold, which will be 0.0010. Similarly, the third smallest p-value, you expect the third smallest p-value to be 3 by 100, right? And you will multiply that with 5% false discovery rate, you will get the threshold accordingly, right? So it will be 0.0015 threshold for third p-value, right? And the threshold for the last p-value, it will be 100 by 100 into q, because you expect the last p-value to be 100 by 100. You expect the last p-value, the largest p-value to be 1. So you will multiply 1 with q, that is your 5%. So the threshold for the largest p-value will be 0.05, right? So this is the idea of doing correction with respect to FDR. So if you set q for FDR method equal to alpha in the conventional method, then you can understand the smallest p-value will be alpha by k, which will be the same as Bonferroni correction, and the largest p-value will be equal to alpha only, which is equivalent to not correcting for multiple comparisons. So you can see in this case, for example, I have set the FDR to 5%, which is the conventional significance threshold. So the smallest p-value will be nothing but 5 by 50, which is the same as when doing Bonferroni correction, and the largest p-value will be equal to 5% only, which is equivalent to not doing any adjustment, right? So that is your FDR. So this finishes the lecture pretty much. This is for this end part is just for revision of interpretation of all the terms that I've told previously. So we'll just revise quickly again. Let's assume we are doing a one single experiment and null hypothesis is true for this one experiment, and the significance threshold is taken to be 5%. So the interpretation of this 5% is that there is 5% probability that p-value will be significant even if null hypothesis is true, and there is a 95% probability that p-value will be non-significant if the null hypothesis is true, right? Now let's say you are doing multiple experiments or multiple comparisons and null hypothesis is true for all these experiments, right? And for each of these experiment there is a certain level of threshold. Let's assume 5%. So there will be a cumulative family wise error rate which will be equivalent to 100 minus 1 minus t to the power 9%, right? Because this 1 minus t will be the true negative rate for each comparison. So 100 minus true negative rate to the power 9, that will be family wise error rate. So how to interpret the t%? The interpretation of t% will be that there are t% of experiments which can have a significant p-value even if nh is true for all the experiments, and the interpretation of family wise error rate will be that there is FWER% probability that at least one or more than one comparison will be giving a significant p-value even if nh is true for all the experiments, and 100 minus FWER% will be the probability that 0% experiments will give a significant p-value if null hypothesis is true for all the experiments, right? Or I can simply say that this much 100 minus FWER% probability that all the comparisons will give a non-significant p-value if nh is true for all the experiments, right? And in case of uncorrected multiple comparisons, we know that when we have not corrected for multiple comparisons, then the significance level or the significance threshold for each of the multiple comparison, that is the per comparison error rate, is 5%. So I can say that when I have not corrected for multiple comparisons, then there at least 5% experiments of all the uncorrected experiments can give a significant p-value even if null hypothesis is true. So you can see here, let's assume we are having 100 experiments, and let's assume that nh is true for all these 100 experiments. Then out of these 5% experiments, so what is 5% of 100? That is 5 experiments. So 5 experiments can have a significant p-value, okay, just by chance, and rest 95 experiments will have a non-significant p-value. So that is the interpretation of 5% when we have not corrected for multiple comparison. Let's say we have corrected for multiple comparison by Bonferroni correction, and you know, in case of Bonferroni correction, we will usually try to maintain the FWER at 5%. So what will be the interpretation of that 5%? It means that there is a 5% probability that at least one or more than one comparison will be statistically significant just by chance if NH is true. And similarly, there is a 95% probability that 0% of these that none of these experiments, 0 experiments, will have a significant p-value if null hypothesis is true in reality. Okay. So what it means here is to put this into context that out of like 5% probability that at least one or more than one experiment will be significant. So what is this A? This A is the number of experiments which have a significant p-value, right, if NH is true. So the number of A will be 1 or more than 1, that is 5%. The family wise error rate is 5%, right, and probability that A will be 0, that is 95%. Okay, so I hope you are able to understand the context of, I'm trying to put this into table to show you the context of the interpretation of these terms, right. So family wise error rate is 5%. It means that the value of A will be more than or equal to 1, that probability of that is 5%, and the value of A will be equal to 0, the probability of that is 95%. Similarly, let's say you have done correction with respect to false discovery rate and not Bonferroni correction. You know, in false discovery rate, you are maintaining the FDR. You know what is FDR? FDR is, let's say false discovery rate is maybe 5%, right? So in that case, A by A plus C will be 5%, right? Because of all the discoveries you have made, how many discoveries are false? That is your false discovery rate. So 5 by 5 plus 95, that will be 5%, right? So out of 100 experiments, 5 will be false positives, right? So this will be the interpretation when we are maintaining the FDR and doing the correction. So when FDR is maintained at 5%, it means that A by A plus C is 5%, or I can also say that C by C plus A is 95%. Okay. So the definition of 5% changes basically with respect to whether it's single comparison, multiple comparison, whether it is uncorrected multiple comparison or corrected multiple comparison. Okay, so just I will again put everything into perspective. For a single comparison, when the threshold is 5%, it means that there is a 5% chance that p-value will be significant even if null hypothesis is true in reality. When it is an uncorrected multiple comparisons and the threshold for each of the comparison is 5%, then 5% of it means the interpretation is that 5% of experiments can have a significant p-value. But when you have corrected for Bonferroni correction, in that case the family wise error rate is 5% now. So the interpretation of 5% changes that 5% chance that at least one or more than one comparison can be statistically significant if null hypothesis is true for all the comparisons, right? And if you have corrected for false discovery rate, then in that, and false discovery rate is maintained at 5%, then the interpretation of 5% again changes. It means that 5 out of all the experiments which are discoveries, 5% experiments will be false discoveries, means 5% experiments will have true null hypothesis even if p-value is significant in these experiments. Okay, so I hope this is understandable. Just pause this video, try to put things into perspective. What is the interpretation of 5% in each of these scenarios? Now we'll do some questions. Let's say you make 10 comparisons and the null hypothesis is true for all the comparisons. What is the chance that none will be statistically significant? So try to pause the video and try to answer these questions yourselves. Basically it is trying to ask you 100 minus FWER, right? If you are making 10 comparisons, what is the probability that at least one or more than one comparison will be statistically significant? That is FWER. And but it is asking you what is the chance that none will be statistically significant. So it is asking you the chance that 0% experiments will have a significant p-value. So you have to calculate 100 minus FWER. So you can first calculate FWER. FWER is 1 minus 0.95 to the power 10, and then you can just subtract that from 1. Okay, so this will be nothing but 0.95 to the power 10. Okay, so that will be your answer to this question. Is the definition of family of comparison always clear? No, as we have discussed before, it is an arbitrary definition. Different people may see the same data and they can apply the definition differently. If you make only a few planned comparison, why don't you have to correct for those comparisons? It makes sense to correct for all the comparisons that we made, whether planned or not. But according to some authors, if there are only few pre-planned comparisons, then it's fine to not correct for multiple comparisons. Okay, so this is a pretty subjective thing on like when we can correct and when not to correct. When using a Bonferroni correction, does the variable alpha refers to overall family wise significance level or threshold used to decide a particular comparison is statistically significant or not? So when you are talking about Bonferroni correction, the significance level is basically the same as FWER, which is usually you control at 5%. Okay, so the terminology basically remains same. The significance level you will still say it is 5%, or the family, basically it is nothing but whatever family wise error rate you want to control at, that will be the significance level, but the threshold for each individual comparison will change. So the per comparison error rate will change. That will be alpha by number of comparisons. Okay, so significance level will remain 5% only, but the per comparison error rate or the threshold to decide whether a single comparison is significant or not, that will change to alpha by k, number of comparisons. Will you know when you have made a false discovery? No, we can never know when we have made a type 1 error or type 2 error. It's impossible to know. You will never know for sure whether null hypothesis is true in reality or it is false in reality. So that's why you can never know whether you have committed a type 1 error or type 2 error. Okay, are there any other ways to deal with multiple comparisons? Yes, there are other ways, but we have not talked about them in this lecture. We have only talked about Bonferroni correction and FDR, false discovery rates. Physicists refer to, so in physics there is another term called look elsewhere effect. This is just another term for multiple comparisons. So in physics they are making a lot of multiple comparisons, and they are also accounting for these multiple comparisons by adjusting the threshold, the significance threshold. Let's say you are making 13 different comparisons. This is something I want you to remember. This looks like something you can remember. Like if there are 13 multiple independent comparisons, then the FWER is about 50%. So there is a 50% probability that at least one of the comparisons out of 13 comparisons can be significant just by chance, even if null hypothesis is true for all the 13 experiments.